Okay. So now that the next step would be to say, well, what about this strain field? What do we learn about this strain field? Well, first off, in the strain field, to be able to compute it we need to know how we relate derivatives in the x world towards derivatives in the eta world, or and psi world. Okay, so in this world we know things are now, let's say take some function x, u is a function of x and y. But we know it's not just a function of x and y, it's a function of x, it's a function of x and y, but I mean, it's in turn, each variable is related to psi and an eta. So that's what we have. And now what I would like to know is, if I want to, for instance, compute some of the strain components, is what is du dx? And what is du dy? What is that equal to? What is that equal to? Well, the one thing that we can ask ourselves is, okay, let's just take derivatives of u up and until the last variables that we can. So that's psi and eta. So u is a function of x, which is in turn a function of psi and eta. So let's just first do that and see what we learn from that relationship. So let's do that. So let's say the derivative of u with respect to psi and the derivative of u with respect to eta. Let's just take that through and see what we learn. Derivative of u with respect to psi is derivative of u with respect to x, then multiplied by psi. So that's just the chain rule that I'm doing here. Nothing fancy here. Really just basic stuff. So u with respect to x and x with respect to psi, plus u with respect to y, and then y with respect to psi. So that is essentially if I want to know how things vary with psi. This u or y is also a function of psi. So that will be u vary with y and y with psi. That's what we have here. And well, the same would just go for this side. I'd say here essentially u with respect to x and x with respect to eta, plus u with respect to y and y with respect to eta. Beautiful. You see that? And so that's what I learned from this. And if that's the case, I can now easily get some relationship out to say, well, these are the du x's and du dy's that I'm looking for. Remember, this is what I would like to be able to know. So there they are. So what do I do? Well, let me just write this also. Sorry, I write it now as it should just be like that, because u is a function of x and y. Okay. But that's essentially what I have there. So this is just partial derivatives because u is a function of x and y. There's two variables that so that's just to make sure that we don't just write it unnecessarily wrong. But anyway, so the bottom line is, if I want to know what is this, I could maybe say let's focus on this part here and isolate what's going on. So I can say partial u, partial psi. So that's the one component, the partial u, partial eta. I'm going to write this as a vector, and I'm going to write now sort of a matrix and pull out all the x dxi's, because there's the du dx's, du dx's and the u dy's. I want to pull that out because that's what I would like to try and isolate. Okay, there's that. So so this multiplies with the x psi. Then this would multiply with this. So what is that? Y psi. Then it's du dx multiplies with the x eta. The uy multiplies with the y eta. Beautiful. Okay, so that's what I have. If I want to have this in isolation, I just take the inverse of this. So multiply by the inverse of this on both sides, and then I have that in isolation. What the hell is this? This is something that you've seen many times before, especially in second year maths. Let me see where I can write it down. It's called the Jacobian. So that is what that is. I'm going to just wipe down here at the bottom so that we can really understand what's going on here. Let me wipe this off. This is called the Jacobian. And so if I want to know what is dx uy, partial u, partial y, I just have to say, well, fantastic. If I want to know what this is, just take the inverse Jacobian, so, and multiply it by this. So I can say to you that partial u, partial x, partial u, partial y. You can see that this is getting hectically underneath. Okay. Partial y. So that's what I have there. Okay, so let's make sure this is equal to the inverse Jacobian. So I'm just going to call this J. This is the inverse Jacobian multiplied by partial u, partial tsar. Partial u. Wow, what is that? Like a y almost. What is going on today? Partial u, psi, and partial u, partial eta. So I've just multiplied both sides. This side with the inverse Jacobian and this side with the inverse Jacobian. This becomes the identity matrix multiplied by that. But this is essentially my first components of strain. So this is not. So this is the components that we can use to compute the strain. Okay, so let's stop here because this is now explain to you what the Jacobian is all about. Okay. And the Jacobian about and the inverse Jacobian, sorry. And then the other thing is that I just want to highlight here that's important is, what about this derivatives of u with respect to psi, u with respect to eta? Well, the u's are just, again, the sum of the shape functions, yeah, multiplied by the unknown nodal displacements of those nodes in the x and in the y direction respectively. So this is what, because we work with the u field, this is only nodal displacements in the y and the x direction, left and right, that matters. But these things we can compute explicitly because we can write down the form of the shape function explicitly. We'll talk about that. I'll just first want to run through this whole thing, and then we're going to derive how those shape functions would look, based on our knowledge from the 1D case. But this is essentially just to make sure that we're comfortable with this. So let's stop here and let's look at what we can do with a complete strain.